All right. So today we are continuing our discussion of stresses and design and strengths of materials. However, unlike the previous lectures, we're actually moving on to Chapter 7, which covers the transformation of said stresses. We went into it a little bit when we were dealing with Chapter 2 with uniaxial stresses, which I'll show you guys a little bit of a recap for how we transform stresses in a uniaxial stress state. And then we'll go further in depth into three-dimensional, well, more so like two-dimensional stresses, because when you're dealing with 3D, it becomes an entire nightmare to the point where it's actually beyond the scope of this class. But for 2D stress transformations, so biaxial loading, shear stress development, we'll cover that, and I'll show you guys a few techniques for how we can really handle it and analyze these stresses at a very high level. So first, let's just consider uniaxial bar subjected to some point force P. We learned last time that we can just basically calculate the normal stress that's acting within the bar, and then by cutting a section at some inclined angle theta, we can determine what the stresses are on a very particular plane. Now, why might this be important? You may be welding two types of bars, and that weld may be at an inclined angle. And so if you're trying to analyze the stresses on that weld, then you obviously need to know what the normal and shear stresses are parallel and perpendicular to the plane in which that weld is connecting, right? And so what we ended up doing is we looked at a very small point in that entire element, and we basically broke down the stresses into three separate categories. There is a stress in the x direction, a stress in the y direction, and then a shear stress. These stresses are all dependent on whatever the cross-sectional area is, the plane of said area, which is why you kind of get that sine squared, cosine, sine, because then not only are you considering the vectorial components of the force, you're also considering the vectorial components of the area, which is why you get that cosine squared, sine squared. Does that make sense, what I'm kind of getting at so far? And so basically, when we consider a stress state and transform these stresses, we break it down, and that's when we categorize sigma x, sigma y, and tau xy. And we denote sigma x, sigma y, and tau xy as what we call the normal in-plane stresses. And then we use y prime and x prime. You guys can see the little primes over there. That's the little dash marks or the apostrophes. We denote those as the transformed stresses. So those are the stresses along a very particular plane that we are interested in. And so you end up with those equations over there for uniaxial tension. Same thing can be for compression. However, what happens when you start loading it in three directions and you're subjecting this bar to three-dimensional stresses? The thing becomes more of a nightmare, and as a result, you cannot use these, because then at that point, it's not uniaxial loading anymore, right? We learned that in many cases, loads can be three-dimensional, two-dimensional, all depending on the type of situation that you're really dealing with. So we need a generalized solution. So this is where we get into our discussion with the general plane stress. Now, when I say plane stress, we're dealing explicitly with, When I talk about plane stress, I'm talking about we're on a 2D plane. So if we had some rectangular cross-section here, you may have a sigma x and a sigma y, and then some tau xy. And then when you transform those stresses, you get the sigma y prime, sigma x prime, and tau x prime y prime. We're not going to be really delving too heavily into three-dimensional stresses, where you may have a sigma x, a sigma y, and a sigma z, and then like tau xy. You might have, tau yz, and then like tau xi. It becomes a nightmare, it becomes complicated, and then some of the techniques that we use to analyze these 3D stresses, you can't really do that, use the techniques that we're covering today to analyze three-dimensional stresses. If you're interested, we could go over it some point after we cover this chapter. It's usually a higher level course and generally requires taking some type of determinants or doing some more advanced math in order to calculate. So let's consider just the same block. It's a planar element, so we're only considering stresses in the x and y direction as well as shear stresses. Now we need equations in order to analyze what these transformed stresses are. I'm going to zoom in here a little bit. Basically, all of these equations ultimately come down to force equilibrium. All right? So if we take the forces in the transformed x direction plane, what we end up with is all of the stresses in x and y multiplied by the areas that those stresses are acting on. So we're going to have some culmination of stresses in the x direction, some stresses in the y direction, and shear stresses all contributing to some force in the x direction. Reason being is because now this x direction stress here, for example, is now going to be moving in some way towards the x plane, if you guys agree with me. The stresses in the x direction are also going to be moving in the x direction, and then tau xy, similar thing. Right? So when we write our equilibrium, we end up with this giant expression, sigma x cosine squared theta plus 2 tau xy cosine theta sine theta plus sigma y sine squared theta. That all just comes from equilibrium. And one thing you'll notice is that one of the assumptions we make, which this will hold true for an infinitely small area, all of the terms should cancel out with each other. So you end up with a stress equation that's entirely independent of what the cross-sectional area is. Because if you remember, our stresses are just a means of defining a force per a unit area. So all of the areas will just end up canceling out through this equilibrium term, which then allows us to write an equilibrium equation in terms of stress, not necessarily force. Right? Now, we may want to rewrite some expression because now this kind of looks a little bit messy. And so what we end up with is basically 1/2 sigma x plus sigma y plus 1/2 sigma x minus sigma y cosine 2 theta plus tau xy sine of 2 theta. And that is basically the transformed stresses along a transformed x-plane, or the x-plane in which we're interested in. Now, one thing that I'm going to note, and I'm just going to have you guys just jot this down as just quick notes really quickly, just because it's going to help with one of the methods in the future. I prefer to call this average normal stress. Right? It's stresses acting in x and y, so it's the average normal stress that's acting in the material. It's the average between x and y. And then this here, sigma x minus sigma y divided by 2, I call that a deviatoric stress, which you could denote this probably using, I don't know. I like to use, what do I want to use? We could call this term C. I think that's what it denotes it as. But it's basically just the true term is just deviatoric stress, which that difference is just basically going to equal some shear stress contribution. It's not really too important right now, but just the terminology is good to note right now. And then lastly, tau xy, that's just tau xy. We know what tau xy is going to end up being because that will usually be given to us. All right? Now, we just derived an expression for sigma x prime. Did everyone get that down, or does everyone need a minute to write it down? Or I also uploaded the PowerPoints online if you guys have access to those. So am I good to continue or?
Just one second.
Yeah, sure, take your time.
The PowerPoint you posted, like some of the lines are like kind of screwed up there.
Of course. All right, I'll be spending some time this weekend fixing it up. Don't worry. I'll make sure everything looks nice and pretty for you guys. I tried fixing the first half of it. The second half is like, I figured I'm not going to get to it today, so I was like, oh, that's a next week problem. Let me know when you guys are ready to continue. Just give me a thumbs up. Awesome. Awesome. All right. Now, like I was saying, we need some other equations because we right now only got one equation to describe what the normal stress is along that x direction, the transformed x direction. So here's another expression just to derive the transformed shear stress, which again comes from force equilibrium. The areas are all just going to cancel out with one another, which is how we end up with a force equilibrium equation entirely dependent on stresses. And what we get is tau x prime y prime is equal to -1/2 sigma x minus sigma y, which again, that 1/2 sigma x minus sigma y we denoted as c, which was the deviatoric stress, plus tau xy cosine of 2 theta. I'll give you guys a minute to write this expression as well, but it's all just the same thing, basically just doing force equilibrium, analyzing the stress equations, and then just manipulating the equations just to get these nice fancy terms. Of course, cosine theta sine theta is just equal to 1/2. Make sense? All right. Now, one last thing. With sigma y prime, we can get the same exact expression using force equilibrium. But one thing to note is that the y and x axes are always going to be 90 degrees with respect to each other. So because of that, you can actually simplify a lot of the equations by just basically plugging in the sigma x prime equation and just now setting that rotation equal to 90 degrees shifted. And what you end up with is basically just the sigma x prime location equation that we had previously derived, but now just with opposite signs. So this was basically just, if you guys remember, here I'll show you guys like a quick comparison on what I mean. So if I paste this in here, what you guys should hopefully note is that sigma x prime and sigma y prime look like identical equations, with the only difference being the plus signs and the minus signs, right? So if you ever feel like you're forgetting the equation or whatnot, just remember that sigma x prime is always just going to be pluses, sigma y prime is just going to be minuses. And then that sigma average will always have the same sign no matter what. And I'll give you guys a minute to write that down. I know this chapter is notorious for equations. I'm sorry about that. These are some of the longest equations in this class, other than the deflection equations that you guys might start deriving for beams later on this semester. So just bear with me with these equations. Some of them are a pain in the butt. All right. So those are the three equations that we use to define a general stress state and to be able to transform the stresses for any particular orientation of that very small point. So one thing to note, it says observe by adding 1 and 2. You can check if your equations are right by just checking that the summation of the normal transformed stresses, they should always equal the summation of the normal stresses. So sigma x prime plus sigma y prime is equal to sigma x plus sigma y. So that's always a good check to perform, because that's just kind of a way of knowing if you're, doing your checks correctly. So the normal stresses are independent of the coordinate system, the summation thereof. All right, and that's basically how you would use, that's basically just the equations. One of the things that I want to do here is right now just ignore that Moore circle terminology, because I'll actually get to that in a second. What I'm going to do is just cut that, and let's just do like a really quick example problem just to show you guys how we would use these equations. All right, so we're given a coordinate system. We have a sigma x, sigma y, and a tau xy. And let's say we wanted to find what the transformed stresses would be if we rotated this entire cube, which is going to be our point of interest. This could be some pressure vessel. It could be a sine. It could be the sine problem that I gave you guys. It could be anything. And when you analyze it at a very small level, you might come up with these stresses. So let's say I wanted to find sigma x prime, sigma y prime, and tau xy prime when, I don't know, let's say we transformed this by a rotation of 30 degrees. So what we should get is basically something along the lines of, whoops, delete that, copy, paste, and it might look something like that. If we cover these out really quickly, actually, let me see if I can't use like, can I change the color to white or something like that? Nah. This would be our sigma x prime. This would be our tau xy prime. And then this would be like sigma y prime. That would be, oh, wow, yikes. This would become, come on. Come on, y prime and x prime. All right. And so this rotation is 30 degrees from what it initially was. All right. How would we find the transformed stresses? What would this look like? I'll give you guys just a minute to figure that out. of sigma y. All right, so let's go over it. Basically, problem should just be a plug and chug. All right, the equation's very straightforward to follow with whatever angle you're dealing with. It's just plug and chug. So sigma x prime is just going to equal sigma x plus sigma y divided by 2. That first requires us to know what sigma x, sigma y, and tau xy are. So, oh, yikes. That is a big marker. So, sigma x, positive 20 megapascals. Again, your sign conventions are very important. Sigma y is going to be positive 10 megapascals. And then tau xy is going to be positive 5 megapascals. All right. So, sigma x plus sigma y divided by 2. That's just going to be the average of the x and y stresses. So you should get 20 plus 10 divided by 2 is 15 megapascals. And that's positive because they're both positive. Plus sigma x minus sigma y divided by 2, which is going to equal 5 megapascals. And then, because these equations are long, I don't remember them. Cosine of 2 theta of 60 degrees plus 5 megapascals for the tau xy sine of 60. Plug this in. Let's see, 15 plus 5 cosine 60. Plus 5 sine of 60. You should go to around 8.714 megapascals. For sigma y prime, it's the exact same equation, just instead it's 15 minus 5 cosine 60 minus 5 sine of 60. So what you should have gotten for this is 21.286 megapascals. Hopefully everyone got that. And then for tau xy prime, it's negative sigma x prime. It is negative sigma x minus sigma y. So negative times positive 5 megapascals. Sine of 2 theta. Plus 5 megapascals cosine of 60.
Professor?
Yes.
Are you in radians or degrees?
These should be. Oh, jeez. How did my. Great point. You should be in degrees. Great catch. You just saved me.
I just had numbers and I got something different.
Yeah. So this one should be 21.83, 830 megapascals. Sigma y prime is minus. Yes, make sure your calculators are in the right thing. 8.1 70 megapascals, and then -5 sine of 60 plus 5 cosine 60 should give you -1.83 megapascals. Is that what everyone gets? Awesome. Now, what if I asked you guys for a different angle? Do you guys want to keep plugging it in over and over and over again? No. What if you had to figure out what the maximum normal stress is? For example, like finding out what the maximum possible value for sigma x prime is, or the maximum possible value for tau x y prime is. Seems like it would be a hassle to have to keep on plugging in over and over and over again, or having to do algebra in order to figure it out. Fortunately, there's an easy method in order to graphically plot this entire thing for all possible orientations. I'll give everyone a minute if they need me to. Am I good to continue, or does anyone need a few minutes? I think everyone's good. All right. So, next slide is basically just analyzing this relationship on how we can plot this entire thing. And what you'll notice is we can geometrically manipulate all of our equations in order to get the equation of a circle. All right. You can follow the steps here, but basically this is where I was kind of like telling you guys like, hey, I would highly encourage you to note sigma average and C, because this is where that term C comes into play. That's the sigma x minus sigma y. The sigma average is just plotted there. And what we end up with is this equation for a circle that's down here. I would say the derivation is not necessarily too important, but more so the steps on how to develop these more circles is really like the key important aspect of it, and just understanding the manipulation between these equations and plotting them as a circle. All right, so when we plot these stress states, we end up with a circle, which then we can basically plot out every single stress state that we care about. In this case, when I was saying what are the maximum stresses that a circle what are the maximum normal stresses that may be undergone by this entire system? Well, that comes from understanding how to use this. All right. So when we're drawing this, we call this Moore's circle. A guy named Moore developed this. We basically treat it where the x-axis is all of the normal stresses that are occurring. So it's a normal stress coordinate along the x-plane, and then we treat shear stresses along the y-plane. And so what you guys will note is that the maximum stresses or normal stresses we can have are really going to be, it's not drawing, come on, here and here. These are the maximum and minimum normal stresses that the system can undergo. So this might be sigma max. We call this sigma 1 and sigma 3. We call these principal stresses because they are the maximum normal stresses that the system will undergo. And then, of course, up here and down here is your tau max, which is conveniently the radius of the circle, which is the maximum shear stress that our circle will undergo. And then from there, that angle theta, the orientation that we were interested in, is the orientation with respect to what we call the origin of planes, which is our initial stress state. So that's not exactly this, right? So don't write that out, all right? Theta is instead the rotation from which an existing stress state may occur. So for example, our previous problem may have had an origin of planes that looked like this. And so if we transformed it 30 degrees, this angle would be theta. I'll show you guys a practical example of how this works coming up. But in summary, we can basically just determine every single stress state possible instead of having to use the equations over and over and over again, and just learn how to plot it. And quite frankly, the steps for drawing the circle are so much easier. The only thing is you got to draw the circles neatly if you're going to be using the circle to analyze the stresses. Otherwise, if you're freehanding them, you're going to get your answers all messed up because it's not going to be drawn to scale. So my recommendation would probably be for homeworks, using like AutoCAD or something to draw it out to scale, and just making sure that you stay really neat with it, because then at least you could get a good amount of accuracy with your numbers. All right, so this is just going to be like an example that I want to do, just to show you guys how we basically use Mohr circle, right? So we're going to use the same exact problem that we previously had, all right? And one of the things that we need to do is first understand the important coordinates of the circle. So what this requires is first understanding what the average stress is, understanding what the deviatoric stress C is, and then, I don't know, let's say we wanted to figure out the maximum radius of the circle, which is going to be R, which conveniently is going to equal the maximum shear stress. Because if you guys remember, the maximum shear stress is just going to occur right up here, which is conveniently the radius of the circle. So sigma average, again, is just sigma x plus sigma y divided by 2. That was what from this problem? It was 15 megapascals, right? The deviatoric stress, that was sigma x minus sigma y divided by 2, which gave us 20 minus 10 divided by 2 is 5. So positive 5 megapascals. But now the trick is, what is the radius of this circle going to equal? Well, let's go back here really quickly, even further here. All right. We know that the stress at some particular point, let's say that our point of interest is like roughly here, all right? That's going to have some coordinate here, and then we can just break this geometry down as a triangle, right? This term here is basically going to be our C divided by 2. Reason being is because if we draw this out continuously, this point here will be like sigma x. This point here would be at some sigma y value. And so that C over 2 is just equal to sigma x minus sigma y divided by 2. Blech. Sorry. That should just be C, because I think we said that C was sigma x minus sigma y divided by 2, right? So ignore what I just said with C over 2. Change that to C, because C is equal to sigma x minus sigma y divided by 2. All right. And then obviously, what's the height of that triangle? That's going to be the y coordinate that we're interested in. This y coordinate is tau xy. So whenever you're developing these circles, you need 2 coordinates more than anything else. You can plot them as sigma x comma tau xy for your x and y coordinates, and then sigma y comma negative tau xy. Why the negative? So that way you can get the opposite location on the exact opposite side of the circle. And with that in mind, what we end up with is C as a horizontal component, tau xy as a vertical component. And so what's the radius of the circle? You can use Pythagorean's theorem in order to find that. So our radius of the circle just becomes the square root of c squared plus tau xy squared. You guys see how I get that? Any questions about that at all? Everyone follow? Awesome. All right, so c squared plus tau xy squared. Oops. We know c is just 5, so 5 squared is 25, plus tau xy is just 5 squared, because again, sigma x is equal to positive 20, sigma y is equal to positive 10, and tau xy is equal to positive 5. So square root of 5 squared plus 5 squared, it's going to give us 5 root 2, which is approximately 7.0711 megapascals. Make sense? Awesome. Now I have atrocious handwriting, so I am just going to skip directly to this point here. I hate how they have the radius here of 10. Oh, wait, hold on. What was the shear stress in this problem? It was 5. This bonehead. He changed the stress. Man, all right. Do not draw that circle. I will draw an entirely new one. Hopefully I can just like change this coordinate. Okay, awesome. So let me, that is so convenient. Yes. All right, so from there, we now have all of the coordinates we need. And I'm just gonna put a mental note here that sigma x comma tau xy is just going to be, oh, whoops. I'm trying to grab this. That's gonna be positive 20, comma, positive 5. And then sigma y, comma, negative tau xy is going to be positive 10, comma, negative 5. All right? So from there, we now have all of the coordinates that we need. So first point, plot sigma x plus tau x, sigma x and tau xy. So you go over to positive 20, positive 5. Coordinate 1 is going to be just located right at that point. That's sigma x, tau xy. From there, go to sigma y, negative tau xy, and that's going to give us positive 10, negative 5. That's going to give us a coordinate point here. This is about to be a tiny ass circle, but don't worry. I will just zoom in on this as much as possible. All right. From there, we draw a line. And that is what we call our origin of planes. All right. That's the original problem, the original stress state that we are given. So this is the origin of planes. From here, we can, I want to see something. Can I just group this whole thing? Because I want to like really try and get this thing really large. Cut. I'm going to make this plot larger so that way we're not like dealing with really small circles. And then each and every single one of these blocks is just going to be 5 megapascals per tick. So that's the scale. All right. So we said 5, 10, or yeah, because we're dealing with 20. So 5, 10, 15, 20. And then 5 was here. Come on. Oops. Here. And then 5, 10, negative 5 was here. And then this was our origin of planes. All right. What you guys will notice is that line goes directly through 15 megapascals. Guess what? That's our sigma average. I'm going to call this coordinate 1, call this coordinate 2, and just mark it out as 1 here and 2 here. All right? From there, we know that our radius has to be, well, let's say we know the radius is 7.0711, but if you guys had a circle template, you could just draw out what the circle would be that connects the point lines together. So I'll take a nice circle here. Let's see, and maybe connect these two together, just like that. And then maybe, how do I get rid of the fill? No fill. And just connect everything just like that. Close enough circle, right? Good enough? All right. Now what we'll find is the radius of this circle should equal that 7.011 megapascals that we previously calculated, which when you measure where tau xy is located, this tau max will equal the 7.011 MPa. Let me erase this. And that's how you would draw Moore's circle. All right, and then from there, we can figure out all of the other stresses that we are interested in. Let's say we wanted to find that term sigma 1 and sigma 3, our principal stresses. All right, sigma 1 would just be right here. Sigma 3 would just be right here. How do you guys think we could calculate those? How would you guys break this down? Yeah.
Just take the average and then plus or minus the radius.
Exactly. So the maximum normal stress, sigma 1, is just going to equal sigma average, which we said was 15 megapascals, plus the 7.011 megapascals, which gives us 22.011 MPa. And then sigma 3 is just going to be the same thing, but instead minus. Which gives us 7.989 megapascals. We call these our principal stresses. All right, so these are the maximum axial stresses, maximum normal stresses you would want to design for. And then obviously you would design this material for a shear stress of 7.011. Now, let's say we didn't know what the orientation is, because we don't know what the orientation is right now for this red block, for the principal stresses. How much do you think we would need to rotate this rectangular block in order to get the principal stresses? What are you guys thinking? You guys would agree with me that from our origin of planes, we would need to rotate it clockwise some angle theta, right? What is that angle going to be? What do you guys think? Yeah.
Is it just the inverse tangent of the tau xy over sigma x? Would that get you the angle?
Shouldn't be over sigma x, but
Or would it be like sigma x minus 15, like minus the average, to just get that distance, or not go calculating?
You're on the right track, yeah. So basically, this angle, theta, tangent of theta, would just basically equal well, if we break this down into a triangle, we know that the height from our coordinate point is tau xy. So tau xy. But what's the horizontal coordinate point of that location? Well, guess what? What's nice and convenient is you can just break this down. And what's the horizontal location? It's C, right? So tangent theta is equal to tau xy over C. And what this will give you is this term theta p, which is the angle we need to rotate in order to get the principal stresses. So theta p is just equal to tangent to the negative 1 tau xy over C. We know tau xy, we know C. So let's take the inverse tangent. Tau xy was 5, and C was also 5. So conveniently, it gives us 45 degrees. Which fortunately, because of the way that I drew this, you guys should at least be able to decipher it was roughly a 45 degree angle. That's just convenience because of this problem, but you guys can see where I'm going with this. Now, let's say we wanted to rotate it to figure out what the maximum shear stress looks like. Obviously, you would need to rotate it 45 degrees the other way in order to get it. But let's come up with a generalized equation for this, all right? So in this case, we would have tangent of theta. Let's say that this was theta 2 and theta 1. So we're looking for tangent of theta 2. And what that's going to give us is just basically C over tau xy, right? This will give you theta s, which is just equal to tangent to the negative 1 of C over tau xy, which, when you plug that in, should also conveniently give you 45 degrees. Now, there's just one little kind of caveat with all of this, is that these equations aren't necessarily inherently true. And the reason for that is because if you guys recall from our previous equations, we had those 2 thetas that were included mathematically. Right? You guys remember that with our general stress equations? It was like cosine squared 2 theta or cosine of 2 theta. Yeah. What this means is this circle, every angle that's in the Mohr circle is technically 2 degrees in the real plane, or half a degree in the real plane. I don't remember the exact thing, but basically the best way to think of this is a circle with 180 degrees in rotation. It's annoying. The reason for that is because once you rotate the stress condition 180 degrees, it just overlaps on itself. So really, this should become 2 theta s and 2 theta p, because theta 1 is just 2 times whatever the rotation is that you conduct in real life. It's confusing, I know, but just take my word on it. So the rotation we would need to rotate it would be 22.5 degrees. And I'm trying to remember this because it's been such a long time since I've actually done it. No, it's right. Yes. Theta P would just equal 22.5 degrees. Now, what this shows us is basically this relationship also, which is important to note, that 2 theta P plus 2 theta S should always sum to 90 degrees, which means that theta P plus theta S should always sum to 45 degrees. All right. Let me just copy this to the next page. And then let me erase all of this. So just give me a minute just to do all of that. Let me erase this just carefully. All right. Now, let's say we didn't necessarily care about what the principal stresses are and we wanted the rotation at a particular angle. In other words, that 30-degree angle. Well, then in that case, what you would need to do is you would need to basically rotate this entire thing here. This angle here would just be 2 times our rotation of 30 degrees, which would give us 60 degrees. All right. Now, if you draw this out carefully, obviously it would probably look somewhat closer to like this, I would say, right? So let me just erase that. So that's, let's say, 60-degree rotation from orienting that block 30 degrees. So that would have given us this orientation right here. So you have to rotate the circle 60 degrees. And then from there, you can just kind of manipulate it in AutoCAD or like do the math to figure it out algebraically. And what you would find is that this value here would be sigma y prime, comma, tau xy prime negative. And then this value up here would be the sigma x prime, comma, tau x prime y prime. Now, just for, I guess, a little bit of comparison, just to confirm, we said that tau xy prime was negative 1.83. So one of these two terms should give us negative 1.83, which, again, I think I just drew the circle wrong. If you were to draw it out in AutoCAD, it would make a lot more sense. So, but ultimately, this coordinate should really, I'd say, probably look closer to like, I don't know, this than anything else. So let me just erase this. I'm like trying to be consistent, but like, yeah. Oops. There we go. And that's what our transformed stress state would basically look like. You would have one of your normal stresses equaling to, where is it? Yeah, 21.83, then 8.17. So that's what this point roughly is. This is that 21.83 term. This is your 8.17. And then obviously tau xy is just tau xy prime. Make sense? Awesome. Now, this kind of does another walkthrough. Again, just the stresses, I think this one and this one were like swapped. So it kind of like messed up all of my values for how the plot was necessarily developed. Let me just add like a little note here, just saying see next page. All right, and yeah, you can follow these steps too, and you should be able to get the same stresses as we previously conducted. The following slides basically talk about the principal stresses. We used Mohr circle to derive the principal stresses, but another way you could have done it is through the equations here, where basically you would have set one of the terms. In this case, we said that the principal stresses, the maximum axial stresses, sigma 1 and sigma 3, were basically along that horizontal line, which means if you look carefully here, that sigma 1 and sigma 3, the associated tau xy for those terms was 0, right? So that's where this assumption comes from in the equation. Where'd the slide go? Here, with tau xy prime equaling 0 for us to determine the principal stresses. Right? And so when you do that, you get these expressions for what the orientation of the planes are, which, again, should be the exact same equation that we derived using just the geometry of Mohr circle. All right? And then, of course, for the rotation, yeah, this is another image just to kind of elaborate how much the circle would have to rotate. And then for the maximum shear stress, again, in this case, you would find sigma x prime, sigma y prime, they should match each other, equaling tau sigma average. Because if you note, for the circle here, the tau max occurs whenever the normal stress is average for sigma x and sigma y. Everyone agree with me on that? So you would set sigma x prime and sigma y prime equal to the sigma average. And then from there, you could just work out everything, and you would just find that tangent of 2 theta s is just equal to the equation that we had previously derived, which, again, when you do all of this, you'll find that 2 theta s plus 2 theta p is equal to 90 degrees, which means that theta s plus theta p is equal to 45 degrees. This is simply just another way of saying that for Mohr circle, this condition here is 45 degrees in the real world. It's confusing, very confusing, matter of fact, but just remembering that when you're using Mohr circle to rotate everything using 2 theta, not theta. Otherwise, you're considering the rotation as half what it should be. Does that make sense? All right. I think this is where I stopped, like really playing around with the fixing the slides. So I'm actually gonna copy paste that. I'm gonna cut all of this, and I just want to have you guys just give it a try really quickly and just tell me what the stress state would be. Like, just draw up the Mohr circle and figure out the principal stresses using like some of the methods that we use. You can use either the equations if you want to. You can use a combination thereof. You can use Mohr circle explicitly. Yeah. And then I gave you guys sigma x, sigma y, and tau xy, just for simplicity. Keep in mind the signs. I'm actually going to pause this screen really quickly, just because I want to take this diagram again. And just move that to here. I'm going to erase all of this. All right, let's go over it before time runs out. All right, so we will first do this with equations. Not going to even be bothered with doing that. It's just plug and chug. I just want to draw the Moore circle just so that way you guys have it, and then I'll clean up the slides so that way you guys have the derivations. I'll clean it up this weekend so that way everybody's got the actual thing, because if I show you guys like this, like half the stuff is missing. I hate the fact that the text is like way too small, so like I said, I'll clean up the slides. But if we wanted to find the principal stresses, we need to know that sigma 1 and sigma 3 occur when tau xy prime is 0. So first is just find the normal stresses. So we've got sigma 1 average, which is going to be 50 minus 10 divided by 2. 50 plus negative 10 divided by 2. So that's going to give us 20 megapascals. Next, we're going to have our C term, which is going to be 50 minus negative 10 divided by 2. Which should give us 30. And then we've got our radius of the circle, which is tau max, which is just 30 squared plus 40 squared, and then take the square root of that whole thing. And we get that the maximum shear stress is 50 megapascals. All right. So if we try to draw this out, we're going to have sigma average at 20. Let's say that's here. Then 10, 20, 30, 40, 50. That means sigma 1 is going to be right here, because sigma 1 we know is just sigma average plus the radius. So that's going to give us 70 megapascals. Sigma 3 is just going to equal sigma average minus R, which will give us 20 minus 50, so negative 30. 10, 20, 30. And then I don't think 1, 2, 3, 4, 5. 1, 2, 3, 4. This is a little bit too short, this diagram, so I'm gonna say roughly here and roughly here, right? Our maximum shear stress is gonna occur roughly right where these dotted lines are, all right? And so once we draw this out, insert shapes with a circle. And then let's scale this down. Whoops. This is the rough circle, roughly. So there's going to be no fill on this. That's our Moore circle, give or take. All right. So our radius of the circle is 50. Our original stress state is going to be sigma x, comma, tau xy, and then sigma y, comma, negative tau xy. So this gives us 50, comma, 40, and then negative 10, comma, negative 40. So 10, 20, 30, 40, 50. 10, 20, 30, 40. It's roughly there. It should be running directly through the 40 line. Again, it's a very rough sketch. Let's see. And then we have negative 10, comma 40, so roughly here. And then when you draw our orientation, let's see. If I can get this like pretty close. There we go. With that being our origin of planes. All right. And then from there, we could just basically figure out everything else. This angle here would become 2 theta p. If we wanted to figure out the angle we needed to rotate this block, this would become 2 theta s. And you can basically plot out everything from there. All right. Now, once we did figure those out, let's say the question asked you, what does the stress state look like? Well, for the maximum principal stresses, what you should see is basically just, yeah, so it should be something like that. Where is it? So for the stress state for at theta p, we should get basically a stress state that, oh wow, I'm adding too many slides. Let's say that's our stress block. We basically will get sigma x. This would become sigma 1 and sigma 3. Right? And so that's what our normal stress state would basically look like. If you wanted to rotate this block, you can if you wanted to. But this is basically the equivalent stress block of what this is for the principal stresses only. And then if we wanted to consider at theta s, then you would have a very similar block here, but instead you would have sigma average, and then this would be tau max. Make sense? So you guys can kind of see that the stress block will change as you rotate it, and just the values of those numbers will change, but ultimately they should all result in some type of equilibrium. And when you sum the sigma 1 and sigma 3, those should equal the sigma x plus sigma y. So if you guys remember, sigma x prime plus sigma y prime is equal to sigma x plus sigma y. In the same way, sigma 1 plus sigma 3 should equal sigma x plus sigma y. And then that should just equal to sigma average is equal to sigma x plus sigma y also, because again, sigma average is just in 2 directions. Any questions about this? I know it's a little bit confusing at times. We'll do more practice problems next lecture just to kind of like really drill it in and maybe do some applications where it's not necessarily just looking at blocks, you know. So yeah. Yeah, that's going to be it for today. Let me know if you guys have any questions. I'll clean up these slides. I've already uploaded homework 4 to Brightspace, so hopefully you guys should be able to do it. We actually got a lot done today, which I'm really glad. So yeah, I'll clean up the slides a bit this upcoming weekend, and hopefully everyone should be able to use them properly.
Go back to the slide we've got one.
This slide? No, sigma 1 and sigma 3, right?
Yeah.
This slide? Or
No, the previous.
previous one? Oh, the derivation? This one?
Yeah.
Yeah. That should say sigma average. You as well.
Thank you. Have a good night.
You as well.